Good afternoon, everyone. Welcome to this webinar entitled Acoustic Output Measurement Process for Diagnostic Ultrasound Systems, presented by Mr. James Gessert and Dr. Nicholas Ellens. The AIUM is accredited by the ACCME. This webinar is designated for one AMA PRA Category 1 credit. By the conclusion of this webinar, participants should be able to understand the measurement process and issues associated with determining the acoustic parameters displayed on diagnostic ultrasonic systems, be aware of important issues that may be encountered during the measurement process, understand key equipment requirements associated with the measurement process, and understand measurement reporting differences between the US FDA and an IEC notified body requirements. As an ACCME accredited provider, it is the AIUM's policy to ensure that contents and quality of this activity are balanced, independent, objective, and scientifically rigorous. All individuals who are in a position to control the content of an educational activity are required to complete a disclosure form. All disclosures are reviewed by the AIUM, and any conflicts of interest are resolved or managed prior to an activity. James Gessert is a partner at Acertera Acoustic Labs, and Nicholas Ellens is an employee at Acertera Acoustic Labs. Darcy Bellido de Luna has no disclosures. At the conclusion of this webinar, you will be able to access the CME test and evaluation located on the AIUM website. Participants who complete the post-test with a grade of 70% or higher will be awarded one CME credit. Credits for this webinar are approved for physicians, sonographers, and radiologic technologists. During today's presentation, if you have questions for the presenters, you may type them into the question box on the right side of your screen. You will be able to submit questions throughout this webinar, but the presenters will not begin answering until the end of the presentation, at which time they will answer as many questions as possible. A recording of this webinar will be available on the AIUM website. And now, we're pleased to present Mr. James Gessert and Dr. Nicholas Ellens.
Hello, this is Jim Gessert. Welcome to our webinar. Dr. Nicholas Ellens and I greatly appreciate your interest. The primary goal of this presentation is to help users of diagnostic ultrasound equipment understand how the displayed acoustic output values, MI and TI, are determined. I will provide a general description of the measurements and requirements, while Dr. Ellens will go through those requirements and the actual measurements in more detail. As mentioned by Darcy, our disclosure, Nicholas and I are both with Acertera Acoustic Laboratories. We design, manufacture, and sell acoustic measurement equipment and provide measurement services. The diagnostic ultrasound has been in clinical use for several decades, and over that time has established an excellent safety records. Measurement standards have been in development nearly as long as the technology itself. Standards are well developed for measuring diagnostic imaging systems. Significant historical events in this field include, as part of medical device amendments to the Federal Food and Drug Administration and Cosmetic Act for the U.S., the ultrasonic devices on the market prior to May 28, 1976 were measured settings, application specific equivalent levels. At a later time, with the goal of providing operators more flexibility in the acoustic output used for measurements, the output display standard was developed. It was originally documented in AIUM NEMA document UD3. The ODS defines the display of acoustic output parameters, giving operators acoustic output information. Now international standards have been developed and are being harmonized to provide uniform information on acoustic output. The most recent event has been the withdrawal of AIUM NEMA UD3, leaving the related IEC standards shown on this slide as a consensus definition of the ODS, or output display standards. Current standards define not only the measurement equipment requirements, measurement methods, and ultimately they also define the specifics of the output display standard, what and how it is to be displayed. The primary goal of measuring the acoustic output of imaging systems is safety. As shown on the slide, there is a baby there. Dr. Ellens and his wife are about to become parents. I believe the image on this slide, of course, is their unborn baby. I believe Nick's personal circumstances provided an excellent example of as to why the display of acoustic output parameters and measurements to determine them are important. To determine parameters that have meaning relative to possible bioeffects of a clinical study is really the primary function of these measurements. The mechanical index is a measure of the risk of a mechanical bioeffect. A primary concern is cavitation. Thermal index is a measure of the risk of thermal bioeffects from tissue heating. Mechanical index. Mechanical index is defined as the peak negative pressure divided by the square root of the acoustic working frequency measured at the depth of maximum derated pulse intensity interval. The mechanical index is a pulse parameter. That is, it can be determined from a single pulse measurement. The rationale for the measurement is that it provides a measurement of the likelihood of mechanical effects caused by high rarefactional pressures, most commonly cavitation. It's worth noting here that inertial cavitation is of significant concern, as this type of cavitation can result in local sudden releases of a large amount of energy. And external reference, it's the same phenomenon that actually wears away the propellers on major ships such as ocean liners due to the significant pressure drops at the edge of the propellers. I believe it's also worth noting that I have personally severely damaged some hydrophones in our laboratory when the gas content in the water we used for measurement was too high, and we measured peak pulse pressures that were only a little bit in excess of those used clinically. It is worth noting also, relative to the harmonization of standards, that one of the significant impacts is by IEC 62359 becoming the primary standard defining the ODS, that now the mechanical index is searched throughout the entire near field, whereas the near field search was limited in the UD3, a prior standard. Thermal index is a parameter based on theoretical models. It estimates tissue temperature rise resulting from ultrasonic heating. A TI of 1 estimates a tissue temperature rise of 1 degree C in the tissue model. It's important to point out this is a model estimate. It is not necessarily directly related to the actual temperature rises that you'll see in a clinical situation. The calculation of TI, or thermal index, is complex. It depends on the target tissue, the target transducer or the transducer aperture, the location, whether the temperature rise is estimated at surface or in depth with tissue, and whether the transmit pattern is scanning versus non-scanning. Multiple models are necessary to characterize this range of situations where acoustic energy can result in tissue heating. While the models themselves make some quite significant assumptions as to heating in tissue to simplify the ultimate calculation of the thermal index, the measurement and calculation process is still quite complex. As I believe is well illustrated by the equations on the right-hand side of this slide, which are not a complete set. The addition of these slides were added primarily to convey the complexity of the determination. The TI process is well documented in IEC standard 62359 and its references. TI determination for the multiple TI model equation requires a set of measured parameters, which is the primary subject of this discussion. These parameters include acoustic power, intensity, which is the measure of power transiting through a fixed physical area, derating factors that provide an allowance for the acoustic attenuation as it transits through tissue, the spatial distribution of the acoustic energy matters, and finally the acoustic frequency also matters. As you may have seen in the mechanical index, that the frequency parameter shows up in many of the parameters. It's worth noting that the power can be measured directly with an acoustic force balance or radiation force balance, or it can be determined from a hydrophone measurement. Acoustic working frequency and intensity values are necessarily determined from hydrophone measurements. Okay, expanding on the sensors required to collect the data. Dr. Harrell presented a webinar in this area a few weeks ago where he introduced a number of basic concepts and provided a nice thorough discussion on the sensors. I'm going to focus on abilities and trade-offs specifically for these measurements. Radiation force balance measures total power quickly, including it can also measure the operating ultrasound system as it's operating with complex operating modes. Can be used for measuring the bounded output power. There's a requirement in the standards to determine the power transiting through a 1 centimeter square area, and this can be done with a mask. There are, however, counters to the efficiency of the radiation force balance. One is that for low output devices, the accuracy gets lost in the noise. The sensitivity is not adequate for very low output devices that are often encountered in used for diagnostic ultrasound purposes. And as previously noted, it cannot make all the necessary measurements. Hydrophones measure pressure at a single location in the acoustic field. It's important to keep this in mind because we're trying to characterize for these parameters the acoustic field in a three-dimensional space. It is necessary for measuring the output waveform to quantify the beam extent, and when scanned across the plane, it can also be used to measure the total power output. I wish to note that for diagnostic imaging measurements in our lab, we very often determine all the necessary values just with a hydrophone measurement, usually because of issues related to the sensitivity of a radiation force balance. It is also worth noting that historically, when we have compared the results that we've gotten, at least within the range of valid performance for both sensors, we've been able to achieve good agreement between power measurements made with the radiation force balance and power measurements made with the hydrophone. This is a picture of a typical imaging measurement system designed to make hydrophone measurements. While we're primarily focused on acoustic measurements, I did want to point out that another key part of the standards requirements is to actually make thermal measurements, literally measure the surface of the probe with temperature measuring devices to verify that there's no danger of burning a patient in contact. And those measurements are also made with the tissue phantom to evaluate the temperature rise within tissue as well. Back to the measurement system. The measurement system consists of a tank of water and a three-dimensional or a three-axis stage for moving the hydrophone relative to the acoustic source or probe or vice versa, and an oscilloscope that serves as the digital acquisition device. The water tank itself is approximately a 0.5 millimeter cube and contains 25 gallons of water roughly. It's important to note that accurate positioning is required because the beams measured are often quite small. Okay, here is a blow-up showing a probe in relationship to the hydrophone. The hydrophone shown is a bilaminar membrane hydrophone, and the actual active measurement of the hydrophone, showing with the pointer here, is in the center of the device, and it is of the order of a little less than a 0.5 millimeter in diameter underneath the little box-like area that you see in the center. As I mentioned, because the beams that are measured can often be less than 1 millimeter in diameter, it is very important to have precise control of positioning to make accurate measurements. And that repeatability is an important factor in making measurements. Okay. Because hydrophones measure at a single point in space, a mechanical positioning system is necessary to maintain precise location to be able to accurately characterize the three-dimensional field. Hydrophone data is collected by a data acquisition system, in the example shown, an oscilloscope connected with a computer and software that usually automates significant portions of the specific measurements. It is important that the limitations of measurement sensors and systems are understood and characterized. These limitations are quantified as measurement uncertainty, which must be reported as part of reporting the acoustic data. Okay, as I mentioned, the measurements are all made in a tank of clean room temperature water. The water should be deionized primarily for purity purposes so that results can be repeated across sites and over time. Degassing is critical because the removal of gas prevents both cavitation, as I mentioned. I personally destroyed a hydrophone, and perhaps even more significantly, small gas bubbles formed anywhere on the device being measured or the hydrophone used for the measurements are incredibly disruptive to the measurements. It's worth pointing out that the strongest reflector that can be encountered in a measurement tank doing these measurements is actually a small gas bubble. Finally, it's very important that the temperature is monitored. Velocity of sound moves in a very predictable manner with temperature, and the velocity of sound is directly used in the conversion of radiation force measurements to power, and also the conversion of pressure or voltage to pressure for hydrophones and pressure to intensity. So at this point, I always found it interesting that I learned that early in ultrasound, one of the manufacturers actually made all their acoustic power measurements in a tank that was warmed to 37 degrees centigrade, which frankly made things really quite difficult, because maintaining a body of water at an elevated temperature is a difficult thing to do and control tightly. So, and I believe that's one of the primary reasons the standards have settled on measurement at room temperature, where it is very easy to get things to have a stable measurement environment. Okay, in our laboratory, hydrophone selection, and I believe in most laboratories, hydrophone selection is a process. The first thing we need to consider is the frequency and likely spot size of the device that we're measuring, so that we can make sure we're using a hydrophone with an effective spot size. The requirements are well defined in the standards that is adequate to measure the device being tested. It is worth pointing out that some of the more advanced systems and super high resolution systems actually are capable of producing spot size focused beam areas that are small enough such that pretty much all hydrophone technology is at least a little bit challenged in making those measurements. For pulse measurements, we always select a bilaminar membrane hydrophone, and this is for a couple of reasons. The primary reason is the frequency response of bilaminar membrane hydrophones tends to be very flat, and therefore provides more accurate information when evaluating broadband pulsed information. We also like to use the bilaminar membrane hydrophones because the stability long-term is quite good for the devices. We have a hydrophone we have been using in our laboratory for over 10 years, calibrating every few years, and the response has never varied on calibration by more than a dB at any frequency over that period. Now, of course, if the waveforms to be measured are very long pulses or CW, you can see looking at the bilaminar hydrophone that reflections and reverberation, providing interference patterns and creating inaccurate measurement results can certainly be a significant issue. In this case, we always choose a needle hydrophone. The fact that needle hydrophones inherently have a frequency response which is less flat than the bilaminar membranes is not an issue when you're measuring CW devices, because of course the frequency response of the devices is very narrow, so you're still able to accurately convert the return signals to an appropriate pressure. At this time, I'd like to turn the discussion over to Dr. Nicholas Ellens, who will go into more detail.
All right, thank you very much, Jim. So I'm hoping to talk a little bit about the details of the measurement process. And this is the stuff that's laid out in a lot of detail in the IEC standards that Jim discussed at the beginning. I'm hoping to sort of skip over the surface to give you an idea of what goes into these measurements, even if the specific details aren't relevant or very important to your day-to-day work. So the first thing to understand is that we take a normal ultrasound probe like the one shown here. We have a linear probe, a curvilinear probe, and a phased array, and they all transmit successive beams, and that's how they build up a two-dimensional image. So here, each of these lines represents one of the transmits, and they're made in quick succession. We take a device like that, and we have the manufacturer modify it for us so that we can make testing, to facilitate testing it rather. And the modification consists of two things usually. One, a trigger signal is taken from the board that does the transmitting and allows us to trigger our oscilloscope simultaneously with the emission of ultrasound energy. And the benefit to doing this is that we can much more easily locate the pulse in each successive time, which allows us to do things like average the signal and really improve the measured data we're getting from our oscilloscope. Most manufacturers also provide a way to limit the transmission to a single line. So instead of making these successive lines or the sweeping line, you just do one line down the center each time, one after the other. And in doing so, it reduces the amount of time it takes for us to measure, that we can just get the one line we measure each time, every time, and then we can make our measurements quickly. Now, in order to make this situation match the clinical situation, we then apply mathematical scaling so that we can represent what's going on in clinical settings based on our single line measurements. So again, we make the careful line-by-line measurements over here, and then we mathematically scale it, knowing the pulse repetition frequencies and the sweeping parameters, so we know what's actually going on in a clinical setting. So in terms of the actual measurement we make, we have an oscilloscope which has a very accurate clock and samples voltage at a very rapid rate. So from our hydrophone, we get a signal that might look something like this, and this is just a simple, probably a 2-pulse excitation of the transducer, and the hydrophone sees it as these series of peaks. And this is a fairly typical pulse. Using the hydrophone sensitivity from our calibration, we can convert this signal voltage to a pressure, in this case in megapascals. So now it looks exactly the same, and as Jim had mentioned, MI is a pulse parameter, so just from this one conversion of signal to pressure, we can now pretty quickly calculate our mechanical index, and that comes from the peak negative pressure observed right here. In order to calculate things like TI and the parameters which involve spatial averaging and other things like that, you want to figure out how much energy is being transmitted into the tissue with this single pulse. So to do that, we square the pressure field and integrate it with some constants, and that will give us our pulse intensity integral. And so you see that over time there's no energy, the pulse is transmitted, the energy that's been delivered to the tissue increases, and then it levels out again, and at the end of this 2 microsecond window, we can establish, for instance, that we've had 2.75 microjoules per centimeter squared of energy has been delivered to that area. Also from our pressure graph, we can perform a Fourier transform and get the same information in a frequency domain. And where this is important is that we see all the frequencies that are present. So in this case, this center frequency is around 10 megahertz, and that's where you get the highest response. But you see that we also have an envelope. So the 3 dB points, which is 70.7% of the pressure, is around, in this case, maybe 7 megahertz, maybe 13 megahertz. So there's a range of frequencies that are present in this single pulse. And where this is important is that we find these negative 3 dB points here and here, take the arithmetic mean, and that gives us our center frequency. And the center frequency is used both in the calculation of MI and TI, and it will come up several times in the duration of this presentation. So the measurement process looks something like this. We first are going to walk you through probe positioning and registration. Second will be the probe alignment, which I'll emphasize the importance thereof. Then we'll measure within a hydrophone, moving it along the acoustic axis out from the hydrophone face to characterize the field in that direction. And then we'll perform a raster scan near the entrance, or sorry, near the face of the probe. And then we'll perform cross-axis and raster scans at the peak and pulse intensity depth, which was established with our acoustic axis scan. So I'll walk you through that step by step. So in terms of positioning and registration, the ultrasound beam is typically directed down or to the side. And this is done so that both for convenience, so you don't have to waterproof the whole device you're testing, you can just submerge it into the water. But it also has the benefit that the sides of the tank offer a more absorbing interface than if you were, say, to point it up and have it reflect off the water-air interface at the top of the water tank. One or both of the hydrophone and test device are mounted in goniometers so that they can be co-aligned. And goniometers are mechanical devices which usually have screws which allow you to adjust the pitch and yaw of the device being held by them. And the key here is that the angle changes without changing the position. So you're rotating the device around the center of rotation located on the transducer face, which allows you to align without shifting. The next thing is that you will place a gauge block, or you could also use a micrometer, but we tend to use gauge blocks, which are very simply blocks of metal of very uniform thickness. We'll place it across the hydrophone and then lower the test device so that it's resting on and flush with the top of the gauge block. Then we remove the gauge block and we've established a known separation between the hydrophone and the device we're testing. And this can be done quite accurately with accuracy of inaccuracy of less than a millimeter. Once we've established this initial offset, we know the separation between the hydrophone and the probe. We then go about the alignment. And so for a typical ultrasound field, the maximum intensity at each depth falls along a single line called the acoustic axis. And this axis is perpendicular to the face of the probe. The proper alignment is essential for a couple of reasons. First, the hydrophone is only accurate when sonicated at a normal incidence. And this becomes especially important as the frequency increases. So shown on the right here is a frequency response. So I have an intensity here as well as an angle left and right of, in this case, it's this is minus 40 degrees, this is positive 40 degrees. And as we rotate the angle of the hydrophone relative to the source, the sensitivity changes quite a lot. So, and then as you see at higher frequencies, at 7.5 and here at 10 megahertz, this envelope gets smaller. And so at 10 megahertz, for instance, a 5-degree error in alignment translates to a 1 dB error in the pressure you observe, which is in this case 12%. And so that's a fairly major error that comes from a misalignment. The second part of alignment is that it makes our measurements easier. So we're trying to characterize a large three-dimensional field with a series of one-dimensional and two-dimensional acquisitions. And this is done simply to lower the magnitude of the information we need to capture to characterize this field. To do a good alignment, it's very important so that we can align both our horizontal and vertical, our parallel and perpendicular axes where we're going to acquire our data going forward. So one of the ways we do this alignment is we will measure the maximum intensity on two planes, in this case one a bit closer to the face and then one out past the focus. And these 2 points in the hydrophone's reference frame will define a vector, and the vector has a few angles associated with it. By using the goniometers to subtract off the angles we observe in this vector, we can adjust, rotate this acoustic axis so that it's now co-aligned with the axis on the hydrophone frame of reference. Once that's accomplished, we then go about carefully measuring the pressure along the acoustic axis. So to do this, we move the hydrophone as close as possible to the hydrophone or to the transducer face without damaging it, and take small steps away from the probe, measuring the pulse intensity integral at each location. So what that might look like is shown by this curve here. Right next to the probe face, you'll end up with a bit of high variability. Then it starts to level out, and you'll get a nice smooth curve peaking a little bit inside of the geometric focus. And the geometric focus is what you might set on a diagnostic ultrasound system. Your peak intensity is a little bit inside of that point, and then it falls off, and there might be some bumps in the far field. We look for this peak intensity, and then we also apply derating. So as Jim mentioned, all these measurements take place in water, and water has almost no attenuation, particularly at lower frequencies. And to account for what this might look like in soft tissue, the curves are derated with a factor of 0.3 decibels per centimeter per megahertz. And this compensates very conservatively for tissue attenuation. Doing this will also move the derated pulse intensity closer to the transducer face than it was in water. The peak negative pressure at the location of highest pulse intensity defines the MI, and that's the value that's single value combined with the frequency allows us to establish the MI for the output display standard. The location of the highest pulse intensity integral, subject to the limitation that it be further than Z min, defines the plane which will then evaluate to calculate TI and then measure the peak spatial peak temporal average intensity, which is also reported. And in this simplified example here, both of those depths would be the same, but there could be depths at which the MI is acquired very close to the transducer face, but the thermal index is calculated from values acquired further out. Once we've established the acoustic axis measurements with sufficient care, we move on to a near-field raster. And to do a near-field raster, a 2D scan is required. So this is moving the moving the hydrophone in a XY step-by-step motion across this rectangle I've shown shaded here. A 2D raster scan is made, measuring the pressure squared integral at each location. And this is used for a few things. First, the total area of the output beam area, it goes into the calculation of Z min, which is the value we use later to establish where we should look for the peak for the temporal or the thermal index. And also we can measure the fluence through this field, and that's used in scanning mode TI calculations. Also with this near field raster is we can look for the bounded power. So this is a 1 by 1 centimeter area with the highest energy fluence. And this is one of the parameters that's used in several of the thermal index calculations. And what that looks like is I've shown this 1 by 1 centimeter area in the orange color here, and it's typically found near the center of the transducer. But for this, you also need to account for the fact that the beam is swept through this. So again, we perform some calculations to establish during normal clinical operation when you want to find the 1 centimeter by 1 centimeter area that has the highest energy output. And that then plays into how those TI models are applied. And this, as a point of note, a radiation force balance can also be used for this measurement. And for a radiation force balance, instead of collecting all of these data and then looking for the highest 1 by 1 centimeter area, a radiation force balance has a mask of an opening of 1 by 1 centimeter, and you can move the mask around, blocking out the rest of the energy, but seeing how much energy reaches the radiation force balance through that masked area. After we've acquired this near field raster, we then go out to the depth where we had the highest peak pulse intensity integral. In this case right here, we perform cross-axis scans, which are shown in these green lines here, as well as a 2D raster scan, which is shown here. The cross-axis scan gives us beam widths at the -6 dB and -12 dB levels, and the 2D raster scan we use to calculate the total energy per pulse, which is the power parameter, which is used in the thermal index calculations. This is an example of what the cross-axis scan looks like, and so you take quite small steps to walk across the beam in both orthogonal directions, so an X and a Y, and you see a response relative to the peak. So at 0 it's at peak, and then you see how fast it drops off, so you can establish the width at -6 dB and the width at -12 dB. The raster scan output looks something like this. This is a typical raster scan output at the pulse, at the focus, at the level of peak pulse intensity output. This is a linear plot of the intensity relative to the peak, and this is the same plot but in a logarithmic scale, highlighting the contours of -6, -12, -18, 24 decibels below peak. So I hope that was a good overview of the calculations and the workflow. I wanted to highlight a few of the special considerations in this process. One is, even with careful alignment, it may be necessary to search at each depth to find the peak, and not just assume that you found the depth and walk straight down. This is particularly relevant at high frequencies, where even a very small shift of kind of a quarter of a millimeter could drastically change the output you're measuring. So what we do, especially with high frequencies, is at each depth we'll do a small search left and right to make sure the measurement we're taking is on the acoustic axis and is at the local maximum for that depth. As Dr. Harrell demonstrated in his previous webinar, spatial averaging due to the size of the hydrophone should also be evaluated, and in many cases compensated for. The measurements, to compensate for this effect, measurements are made close to the spatial peak, so shifted slightly away from the spatial peak in both orthogonal directions. And this can give us an idea of the underestimation due to the finite size of the hydrophone. And you can apply a correction, so you can basically apply a scaling factor to compensate for this underestimation that your spatial averaging has resulted in. The Fourier transform is used to find the center frequency, as I discussed earlier. And this frequency is used to give us the derating factor. So if you recall, the derating factor is 0.3 decibels per centimeter per megahertz. And that per megahertz means that it's multiplied by the center frequency. And so that's significant for establishing the depths you use to measure both for the MI and TI. The acoustic wavelength also determines the step size we take for both the raster and cross-axis scans. The center frequency is also used to apply the appropriate hydrophone calibration coefficient. And you can do this in two ways. Both are permitted by the standards. One is to simply take the center frequency, use a lookup table to take your hydrophone calibration factor for that specific frequency, and multiply the voltages you receive by that factor. Another way, which is a bit more complicated but also more accurate, is to perform a deconvolution, which accounts for the energy in the spectrum which is held in different frequencies. So it's a bit more complicated, but it gives a more accurate conversion from your voltage to pressure. Another thing we use frequently in our lab as a helpful cross-check is to measure it with one hydrophone and then measure the same place with a second hydrophone and compare the output from both. And this serves as a rapid way to confirm that it's a sort of a quick sanity check. Typically, if you see values that differ by any significant amount, you might think that the hydrophone's broken, but more often than not, it's indicative that you've made a mistake in your measurements and need to go through your setup again. And so it's just a very quick and easy way of testing giving a sanity check to your data. So that was the measurement process. Again, I went through probe positioning, registration, the probe alignment, particularly important at high frequencies, the step-by-step measurement along the acoustic axis, moving from the face outwards, the raster scan close to the probe face to characterize the output beam, and then the measurements you make at the peak pulse intensity depth of the cross-axis as well as the raster, and which gives you information which goes into the thermal index models. So to that regard, we take these raw data and put them we use them for calculations and the creation of reports that are then given to regulatory bodies such as the FDA. So the main end-use parameters are the MI, TI, and the spatial peak temporal average derated intensity, ISPTA.3. In addition to these calculations, we also need to consider the effects of the uncertainty, which I'll get to in more detail in a moment, as well as conduct sampling statistics to see how well we're representing a population of ultrasound probes with a measurement of just a few. In terms of uncertainty, there are two types, type A and type B. Type A uncertainty is the random variation between probe samples. We assume that it's normally distributed, and we use 3 or 4 samples of each probe to make these measurements, and then look at the population and see what our standard deviation is. The type B uncertainty is systematic to the apparatus, and these are usually assumed to be rectangular distributions, and they must be adjusted so that you can combine them appropriately with the type A uncertainties. Examples of type B uncertainty include the hydrophone calibration, the accuracy of the oscilloscope, temperature measurements and how they play into various parts as we previously discussed, the spatial averaging based on the finite size of the hydrophone, the effects of nonlinearity, which particularly is important for the hydrophone calibration, as well as the motor position accuracy. So with regard to uncertainty, it is assumed that the source of uncertainty are uncorrelated, and so that the different uncertainties can be combined in a root sum squared manner. And there's a slight difference here in how the FDA and the IEC want these uncertainties reported. The FDA limits are based on a maximum calculated using only type A uncertainty, and this is allowed by the FDA requirements if the type B uncertainty is less than 15% for pressure and 30% for intensity. The IEC report, conversely, combines both type A and type B uncertainties into the determination of the statistical limit values. So where this is different is that whereas the ODS or rather not even the ODS, but for the limits for the FDA says that the limit must be below, for instance, an MI of 1.9. That number is only including the type A uncertainty so long as the type B uncertainty is below this threshold. Whereas the reported IEC values would include both type A and type B uncertainties. Finally, the output display standard requires that any system that can exceed an MI or TI of 1 must display the ODS values for any value that exceeds 0.4. And again, this is so that the operator can apply a LARA, so give as low as reasonably achievable ultrasound radiation or ultrasound transmission to the patient. For a general purpose ultrasonic device, this type of measurement requires a lot of data to fill the ODS tables, which are what's displayed in the ultrasound images, as you saw at the beginning of the presentation. And this is, the regulatory reports only want the worst case scenario. So in a regulatory report, you would make all these measurements, find where your MI or TI are highest, and give a full data set to the reporting agency, such as the FDA, of the worst case. However, in order to fill out all that's necessary for the ODS, you need to perform many more measurements at each of the different system settings and system modes, including combined modes, so that you can accurately fill out that ODS measurement so that it can be, so what's displayed will reflect what's going on in a clinical application. Finally, in terms of FDA submissions, the FDA offers two tracks, track 1 and track 3, where track 2 no longer exists, and that's a historic anomaly. Track 1 does not require the output display standard, and instead it has specific MI, ISPTA, and ISPPA, which is pulsed average intensity. It has limits for each of these parameters, which depends on the use case. So, for instance, peripheral vessel imaging, ophthalmic imaging, fetal imaging with, say, fetal Doppler monitors, things that are much more straightforward, that aren't as versatile, that have fewer modes, could go under the FDA track 1. And these devices have to have a manufacturer supplied. In the manual, it'll have to clearly dictate where this is to be used, and the manufacturer will ensure that for that use case, the MI, ISPTA, and ISPPA do not exceed the limits provided. Track 3 is more of the conventional system which most sonographers are used to seeing, and that does require the output display standard. The overall limits to MI are 1.9, ISPTA.3 is 720 milliwatts per centimeter squared, and ISPPA.3 is 190 watts per centimeter squared. And these are the limits that the system cannot ever exceed, although, if again, based on a LARA, the ultrasonographer is encouraged to use lower values, and that's often encouraged by the manufacturer by simply how the presets are set up. And again, this is the typical track for conventional diagnostic ultrasound probes. So that concludes our presentation. At this point, we'd be happy to accept any questions. So I think we'll give a little bit of time for anyone who wants to chime in, and I believe you can, on the right side of your screen, if your screen looks like mine, there's a box where you can enter your questions. All right, sorry, it's hard to see these a second. All right. Okay, here we go. So the questions have come in. Sorry about that delay. So the first question is, since this testing is in water, how does it compare to soft tissue in diagnostic use?
It is very comparable. The acoustic loss in soft tissue is compensated for conservatively mathematically. The other significant difference is the velocity of sound, which moves the focus around, but these differences are not significant. I believe the measurements made in water are really quite comparable to what you're going to run into in tissue.
Okay, and the next question is, can you review the TI values? And so the absolute limit on TI is 6.
Well, yes, the FDA requires you to contact them for with a specific discussion as to why you would need to exceed TI of 6, noting that nominal body temperature at 37 degrees C with a model predicting a temperature rise of 6 degrees C could theoretically get you to a tissue temperature of 43 degrees C, which is the level at which tissue can ultimately undergo permanent tissue damage.
Next question, it says, what mode is used in testing? And this very much depends on the system under test, and sometimes it's a conversation with the manufacturer. But basically, we want to find a mode which accurately represents the normal sonication mode used in clinical settings, but simply limited so that it's not steered, so that we can get the same single transmission each time. And so that's I hope that answers the question. So the mode is, go ahead.
Okay. Another way to look at the question is basically on a clinical system, absolutely every mode that is going to be used in clinically must be thoroughly measured and reported.
So the next question is, why do devices specific to an organ need to follow different limits than a versatile system, track 1 versus 3? The track 3 limits may be higher than 1, especially cardiac.
Okay, this gets to history. The application-specific limits were legally defined based on simply evaluating all the systems on the market. I'm not aware of any more specific rationale than these levels were okay at the time, so they were approved as part of the original track 1 definition. To then allow users much more flexibility is where the output display standard came from.
So the next question is, it says, I understand just measuring is not adequate. One needs a software tool to convert the measurement to the indices, right? And that is correct. So I hope that we've sort of laid out that process, and I can go back to a slide in a minute.
Yeah.
Let's see. This is sort of, I hope gives you a bit of an answer to that. So the measurement is sort of these 3 steps here. The measuring the pulse intensity along the acoustic axis, the raster scan, the probe face, and the cross-axis scan. And those are the actual measurements we're making. And the rest is, I mean, we use a software tool, but in theory one could also do it on paper. And that process is laid out very clearly in the IEC standards.
Yes, and it's worth pointing out in all the measurement reports we produce, one can literally take the data from our reports and using a hand calculator and Excel files, etc., manually go check all the calculation results if you desire.
The next question is, do you recommend color Doppler on the fetus? And
that's a clinical question that I believe we are not the correct audience to ask.
Yes, I concur. The next question is, which track can be used for shear wave elastography, and what would the limits be in the case of shear wave elastography?
That's a very interesting question, but to this point, all utilization of shear wave elastography has been commercialized in systems that are, at least for the US FDA, track 3 submissions.
And so the next question is, I found most manufacturers don't require ongoing testing. Do these parameters change as the machine ages over time?
That is an excellent question. In actuality, specifically the FDA does require the manufacturers to monitor their manufactured devices over time. Now that's different from, say, clinical life applications. There are no requirements to directly, continuously monitor a device through its clinical life, although it is worth pointing out there are no absolute guarantees, but the most common things that go wrong with clinical systems in utilization will tend to make the acoustic output go down, so that the concern over what happens with systems over clinical life is more one of clinical accuracy and clinical effectiveness, and not so much a concern that you'll be exposing patients to excessive acoustic output.
So the next question is, it says, when passing through considerable fluid paths, such as the bladder or amniotic fluid, the derating allowance would be inappropriate, and one could have an MI greater than 1.9 despite display level less than this. And and in theory that is true. I think the mitigating factor is that the derating factor of 0.3 decibels per meter per megahertz is quite conservative, and so it's higher than passing only through, for instance, bladder, but skin is much higher, probably 4 or 5 times higher than that. Yes. And then the layers, in order to get to the bladder, you're passing through connective tissues, fat, muscle, all of which have higher levels than 0.3 decibels per centimeter per megahertz. So in that regard, there could be a case where it would be higher, but I think it would be, by using a conservative choice of derating factor, that's rarely going to be an issue or a concern. Yes. And at this point, what the final question is, unless someone hops in quickly, it says, who supplies the software? And I guess that we're limited there in our disclosure. We do work for a company that supplies that, but again, based on our disclosures, I don't want to provide any undue influence to that regard. We do have another question. Many manufacturers won't even let you go to 1.9, limits to 1.3, 1.4, no matter how much you turn the power knob. And why is that?
I believe most manufacturers tend to be a little bit conservative relative to the limits, and therefore, and sometimes technically it's just not practical to go to levels that are higher than 1.3 or 1.4, given the limits of the hardware that generates the signal. The high voltage supply of the ultrasound system may not be adequate to go to a higher level than that on a particular probe.
And it's also, the ODS value is showing you the mean. So if they have high variability between probes when they're being tested and the standard deviation is higher, they might be coming up against, they don't want to give an output which with the variation does get higher. So they're showing you the mean value, even if the true value might be slightly higher.
Right, that's an excellent point. The ODS values displayed are the mean or average expected values across all probes and equipment distributed to users.
Next question is, how do you get a triggered signal from a clinical probe? And in this case, that is an issue, but really that generally requires input from the manufacturer. So they basically need to build us a special version or a variation that either coming out of the probe has a dedicated line, or from the system that's sending the pulse would give a separate output so that you can get a trigger one way or another. So in this case, we're testing probes that have been slightly modified and have a slightly different manufacturing pathway than the system that you would see in a clinical setting. So that closes out the questions I have. So I think.
Okay. So I'm going to jump in here, if I may. I'm just going to say thank you very much to our presenters. This was a wonderful presentation. And on behalf of the AIUM, our thanks to all of you who participated in today's webinar. Please remember to complete the post-test and the activity evaluation. We hope you enjoyed this presentation and will join us again for future webinars. So long, everyone.